Hello, I'm Ahmed Fatit from the Biomedical Image Analysis Group in the Imperial College London. It's my pleasure to present our work in collaboration with King's College London. It's entitled A Deep Learning Approach to Segmentation of the Developing Cortex in Fetal Brain MRI with Minimal Manual Labeling. The Developing Human Connectome project aims to make major scientific progress by creating the first 4D connectome map of early life, and what this paper focuses on is segmentation of the developing cortex in fetal brain MRI. So within the context of this paper, our long-term goal is to develop a comprehensive pipeline for the segmentation of fetal brain MRI. This would take in a 3D scan as an input and ideally give back accurate segmentation maps of tissues of interest. These would be structures that are perhaps of direct interest to the connectome, such as the cortical gray matter and the white matter, but also ideally would want the segmentation of structures such as the CSF, ventricles, brainstem, etc. And ideally would want the system to work on any fetal scan regardless of gestational age. This presents a key challenge though, because unlike adult brains, fetal brains tend to show rapid changes in morphology, which take place over narrow timescale. So as you can see in the figure, fetal scans at very young ages, around 24 weeks of gestational age, tend to have very smooth structures. And as the fetus develops, the brain structures become less smooth, but more and more convolved. But one really attractive option is to use deep learning, which is directly relevant to MIDL, in order to develop such a system. But deep learning is very data hungry and will require lots of manually annotated images in normal settings for training. Ideally hundreds of slices from different gestational ages. And there aren't really large public data sets that I know of that we can leverage and avoid the issue of ground truth. So essentially in our paper, we show how deep learning can be used to carry out sensitive 3D segmentation of cortical gray matter in fetal scans. And our key contribution is to carry this out with minimal manual labeling. In essence, these are the main steps. We first apply an algorithm called DrawEM, which was developed by one of our colleagues for neonatal imaging. We actually apply it on fetal data to generate 3D weak labels. We use a fetal atlas to generate those preliminary labels within this DrawEM algorithm. This is then followed by a manual QC step to make sure that we only include scans that were segmented well. We then train a 3D neural network, a multi-class network, using those scans that pass the QC step. And we apply the network on some of the data, but we only give a sample of the 2D slices output to our colleague, an expert annotator in King's College London, who's based in St. Thomas Hospital. All in all, there were fewer than 300 slices that we used for refinement. So the expert annotator then refines those slices, and we use the refinements to feed back into a 3D network that's dedicated just for cortical gray matter. So essentially, we use a 3D model to perform 3D segmentation, but we only require the manual labeling of small subset of 2D slices. In terms of deep learning architecture, we use DeepMedic, which was developed by our colleague Costas. Here we can see an example sagittal slice that was presented to the expert annotator with a focus on cortical gray matter and how she's refined the segmentation to address different issues such as over-segmentation. And this is an example of how the model, our final model, would perform on a completely held out scan. In this case, it's a 28-week gestational age scan. So now you can see the softmax output of our model. And this is the thresholded segmentation of cortical gray matter. Thank you very much for listening, and we hope that you found our paper useful or inspiring.